Hello, everyone. My name is Anton. I'm a CTO and co-founder of development company Spiral Scout. I'm dealing with enterprise development for around last 14 years with main stack in PHP and Golang. And I'm the author of open source products such as Spiral Framework, RoadRunner, and Cycle ORM. In today's presentation, I would like to touch multiple points about PHP lifecycle, how we can speed up our applications and gain additional abilities by daemonizing or moving to long-running approach. And also would like to showcase how you can actually build your own application server to achieve such goal of daemonizing of PHP application. And also show a few of the interesting use cases, what can be done using a combination of PHP and Golang via application servers such as RoadRunner. Today we have two simple goals for this presentation. Number one is to gain pure performance. We do know that PHP can work faster than it typically runs, so our goal will be to speed it up as much as we can, eliminate 502 errors, and reduce costs for our infrastructure. In addition to that, we would like to get access to some additional practices. Specifically, we want to simplify some parts of our PHP code base to make it easier to run for long-running applications. We want to simplify DevOps, deployment, and containerization of PHP applications. And also, we want to find more ways how to run PHP. Specifically, we want to treat PHP rather than just a simple web language, more like a business block which we can put to any processing pipeline. To start, let's review a simple approach. Or approach which we currently use to run and execute PHP applications. If you review most of your applications on any framework, it's typically going to look like that. We're going to have a single entry point, which is ELSA initialization of your script. This is going to set request parameters more like a part of the system, get, post, cookies. After we get in these parameters, we're going to bootload all our code using Composer most likely. It's going to load common libraries, it's going to use framework libraries, user libraries, then it's going to perform some routing, then it's going to execute our code, and then it's going to die. Our process is going to be completely eliminated and start over again on next request. For the last years in PHP, we found multiple ways how to optimize it, and the easiest one for us is to actually implement lazy loading. Specifically, when our domain layer requires some library, we're only going to load this library on demand. We are not going to load them all while kind of booting up our framework. With preloading approach, it's changed a bit. We can now put them to the warmer cache, but the principles are about the same. In this case, we rely on a framework to do this operation for us. We rely on op cache to make it faster. And in general, it helps us to reduce latency and improve the performance of our application. We can go to the bit more complicated approach of using caching. In this case, we introduce a warming up stage of our application. We're going to warm up roads, compile them. We're going to compile the container, compile the ORM schemas, and et cetera, and et cetera. And again, this is going to help us to reduce response time and speed up our application. However, it is going to introduce a bit of additional complexity to our application, since we have to remember that we have to invalidate cache when something changes. If you review this approach from the runtime perspective, it's going to look like that. So entry point, a bunch of initialization, generating response, and exit point. This approach has a couple benefits. First of all, it's very simple. So we don't need to worry about memory leaks most of the time. We don't need to worry about race condition, deadlocks, except for resources. Again, we don't care if anything left in memory. It's going to be completely eliminated. So we can just write simple code, think less, and it's going to work. It's PHP at the end of the day. However, this approach introduces additional overhead. It's pretty obvious overhead. Number one, we just cannot use memory since it's going to be wiped. We have to be creative and use some external key value storages, maybe some shared memory packages, something like that. We cannot rely on keep alive requests. We can in some extent for the database connections, but for example, if you want to open the socket connection to another server, it is going to be closed after every request. So you will have this overhead on every application execution. And obviously, this model involves a bunch of redundant I/O and CPU work, since on every request, we have to load our code, execute it, and upload it from memory. Typically, this approach works like that on a server. We have an Nginx as ingress server. It handles some of the static requests, some of the proxy requests, and then for the application, it just delegates execution to PHP FPM, which is process manager, which delegates it to the free or newly created PHP worker. Once worker done, we have to start over again. So in this case, we have one request, one process, one desk of this process. The downside of this approach, obviously, not only because it's slow, but because you don't have that many options how you can customize it. You can't use PHP process for something more than just a HTTP request. And furthermore, it's very hard to tweak your application when you have different use cases. It can be a very heavy SSR application, or it can be a very light API application. In both cases, you can't split it. You can't split worker configuration on PHP FPM level, so it's going to work identical. So what can we do to improve such approach and get more performance? First of all, we can obviously speak to the language itself. Always make sure to run op cache on production. That's kind of mandatory rule these days. You can also use preloading. Now it's live, so you can pre-cache some of the libraries, pre-warm up them, and it's going to, again, give you some performance benefits. And with PHP 8, we now have JIT, so there's additional performance benefits which you can use by simply upgrading to the latest PHP version. You can go to the bit more radical direction, and you can change stack completely. For example, you can run to alternative VM machines, HHVM from Facebook, KPHP from Contactor, or maybe just recompile your code to .NET using PHP. Some may just scream, okay, let's just rewrite everything in Rust, but that's unfortunately not what business want, but that's another approach. Or instead of doing something, we can redo it completely, and we can actually eliminate the whole bootloading phase of our application. We can eliminate process destruction, and we can start using PHP memory in the process as it's intended to use, to cache some resources between the requests. To do that, we have to daemonize our PHP application or PHP worker. And to do that, we need to move our entry point after the initialization of our application deeper into the project and create a so-called primary loop, the thing which is going to be accepting requests, passing them through the code, and basically generating response. In this case, we are not destroying the process after every request. We're reusing it. It has few benefits, major benefits. It's much faster. It's less memory consuming, and we can reuse open connections between servers, which is very great for the distributed applications. By daemonizing the application, we can also open additional doors how to optimize it, and specifically, we can use the principle of essentially free bootloading. Since our process initiates only once, within the whole runtime, we can treat this time as free time, because we don't care if initialization is going to be done within a second, 5 seconds, maybe even a minute, but a minute is going to be too much. In this case, we're only going to focus on optimizations done in a runtime part of our application within primary loop. This means that we can move all of the library loading, we can move all of the in-memory cache initialization out of this phase. We can completely eliminate lazy loading, in fact, and do all of the things before we actually start consuming requests. Things such as configs, ORM, schemas, caches, templates, all of these things can be done on this phase. And in this case, we can also start using singletons, not classic singletons, but singletons within container to reuse already warmed up services for the requests in our application. We can compare two models. On the left, you can see the model with daemonized approach. And on the right, you can see more classic model. And in this case, we have an interesting kind of use case that daemonized approach in general going to be slower to give you the first request response, because it also needs to do some extra work to bootstrap and heat up your application. However, all requests after that are going to be performed much faster, since this work don't need to be done again. The application on the right, which is classic approach, is typically going to be responding faster on a first request, but it is not going to be speeding up on the next request after that, since the same work should be done over and over again. In general, the approach on the left allows you to speed up your application to 10, 20 times easily, depending on the amount of libraries and amount of business code you have in your application. So it's a very, very performant, efficient way to run your code. However, obviously, the free cheese can only be in a mousetrap. So there is multiple things which we need to remember. Number one, memory leaks. It's a very obvious thing. Everyone has memory leaks. We are not unique. In every language, you're going to meet them. So the general rule is, well, write a code properly. Don't use global context. Don't use global variables. Make sure that everything stays within the proper scope and you clean it up properly. In many cases, you cannot do that. So if you want to run your application reliably, it is going to be mandatory to have some kind of monitoring enabled on the server side to make sure that if script leaks, we can gracefully replace it with a more fresh copy. More complicated error and more complicated problem is related to the state pollution. When some of the user data actually stays in the memory between requests, that's a very, very critical error, and it may lead to the private data leaks. It may lead to the security breaches and etc. So make sure that you always close the user session. Make sure that you do not forget to clean up the user objects somewhere in a global variables if you use them. It's a very important thing to take care of. And the last one is resource locking. Since your workers or PHP scripts run in memory indefinitely, they are going to be locking some of the resources, for example, logs. So make sure that you properly build your code to free them when you don't need them. Otherwise, no one else will have an access to them. So let's take a look how we can actually implement such daemonized approach in PHP in the modern days and what options we have. Option number one is to use non-blocking approach. You're probably already familiar with that. This is approach which brought us by React PHP. In this case, the application and the server is the same thing. We, again, bootload and bootstrap it just once. Then we create a socket listener within our application, and then we process all of the incoming requests inside the same process using event loop or some other approach. The benefits is that you have no overhead between passing requests from the server to your code. The downside is that most likely it's going to be problematic for you to use SPL libraries and libraries you used to do, because database connections should be changed to async mode, and a lot of things should be done differently than you used to do. You can use multiple solutions on the market to implement such thing. It's React PHP, it's Swooly, it's AIM PHP. All of them implement more or less the same model. However, probably Swooly is going to be the different one, which is doing it on much different levels. Specifically, they implement server directly as PHP extension, which essentially gives you the best possible performance optimized way to run your application. However, it has its own downtimes, at least in our use case as well, since it's not modular, it's library, not a framework, it's written in C++, and it basically combines application into one process. So in case of failure in one of the business level, you have a chance that your whole server will be down. Alternative approach is a bit different. In this case, we do not create a socket listener inside our application. Rather, we create multiple workers for our application, which now are going to listen for the incoming data from the parent server. This approach has few interesting benefits. Specifically, you can use it without changing any line of your code. Obviously, if you have no memory leaks. You can use all the SPL libraries, all the existing ORM and debug libraries as you used to do. It essentially works as typical PHP, no differences. The only change is that now your request comes to your application somewhere closer to the HTTP kernel or PSR 7 generator within your code. Again, it also can have some memory leaks, so that's a common problem for long-living applications, but you can solve them by simply checking your code. The downside of this approach is that because the requests are coming from external application, from the server or application server in our case, we are going to have a small overhead on IPC calls. So just keep in mind that during some ultra performant endpoint here is not possible. But since our applications are already heavy, you're most likely not going to notice much difference anyway. From existing solution here, we can use PHP PM. That's a fairly old implementation at top of React PHP. It's done directly in PHP, and it runs as a separate process manager which listens to HTTP, and then process requests to our workers. Unfortunately, in our use case, it didn't work. It was too slow. It has some memory leaks and doesn't work on Windows when we tested it for the first time. So in our case, let's try to do something more, and let's create a proper application server to be used with our PHP applications. So before we're going to do that, we need to set up some expectations and find a way to properly design it. So number one, we want to create an application server which is going to work with almost every major framework on the market. Thankfully, most of the applications now has request response abstraction, so it shouldn't be the problem. We want to separate PHP processes from the application server processes and gain ability to have hot reload, hot deploy, and proactive monitoring. We want to make sure that if PHP process dies, nothing happens. Server just create new one and continue to move on. We want to make sure that we can achieve high performance and very high stability. We need to handle errors on all the ways in to our workers and back. We want to use PHP more than just HTTP endpoint handler. We want to use it for much more complicated endpoints, and I will speak about them later. So we want to treat PHP inside our application server more like a business block, which you can embed to any processing pipeline, and it has to work everywhere. In addition to that, since it's an application server, we need to find a way to build an architecture in a way so we can extend it and modularize it very easily. As you probably already noticed, our choice was a Golang to use to build such application server. And now I will speak to you how we actually did it, how we built an application server called RoadRunner, and what are the functional parts needed to do it by yourself. So if you decide to build an application server, you need to solve multiple high-level problems. Number one, you need to find a way to actually communicate between Golang and PHP process. So you need to implement IPC protocol. There is multiple ways how you can do that. You need to implement the subsystem, which is going to be responsible for the process managing, creating, destroying, monitoring PHP workers, having a pool of them so you can use from them. You need to implement one of the most critical parts of the application server and performance sensitive, which is load balancer, the system which is going to receive the task from HTTP gRPC endpoint and find appropriate free worker to pass it to. You need to implement, obviously, the HTTP stack itself. And then at the end of the day, you also need to make sure that all of these things done in a plugin compatible way, so you can shuffle parts around, tweak them, add middlewares, and add different configuration options. So problem number one is inter-process communication. We have multiple options. First option is to actually embed PHP into Golang. That's a bit weird approach, complicated, but it might give you interesting performance benefits. We decided not to go this route, but there is existing product, experimental product, which is doing that, so you can check it out. You can actually share memory between processes. This is doable, fairly complicated. In fact, we're actually going to do that in RoadRunner 2.0. But for now, in RoadRunner 1, we actually decided to skip it for now. It's fairly complicated since you need to use operating system specific methods, semaphores, and in general, it just requires a bit more configuration. We decided to go to the simplest possible way, and specifically, we implemented transfer protocol using standard pipes or using sockets, Unix socket or TCP sockets. In our case, we want to make protocol as easy as it possible. We want to have it minimal overhead. It should be able to process, to pass any binary data. It should work in both directions, include error detections, and in our case, we want to be able to implement it on PHP with no extensions needed, just using SPL tools. We implement such protocol, at the moment, it's GoRich version 2.0. We already have 3.0. It's very simple NetString-like protocol. It has fixed header, which defines the size, define the error correction, some frame type, like it's error control, maybe stream of the data, and data itself. Fairly simple. I'm not going to be describing how it works. It's You just send a frame, read the size, and read the rest. Implementing of such protocol is fairly easy thing. On Golang, you can use default tools like IO libraries, like net libraries. On PHP, it's pack and pack functions to work with binary data, streams for the standard pipes, and sockets for TCP and Unix sockets. The interesting side effect which we found after implementing such protocol is that it actually appeared to be very easy to invoke any Golang code from PHP application. So that was one of the first use cases which we had, moving some of the business code from PHP to Golang and then invoking it via RPC method. In fact, in our country, one of the largest news portals using this approach to parse BB codes for their forums, they found out that using a library from Golang is magnitude faster than using the same one in PHP. So IPC overhead in this case doesn't play a role at all. The next part of your application server after you have IPC is to actually implement process manager. So in this case, you need to make sure that every PHP process has a bunch of instruments put around. Specifically, you need to collect logs from SLDR. You want to see what's happening inside. You want to observe the memory consumption. You want to count how many requests this worker already handled. And all the communication, well, can be done with same IPC approach, which I described earlier. Important note that the worker should be able to handle only one request at the time, so it works in the blocking mode. In this case, you're not having any issues with concurrent requests. You're not having any issues with data overlapping. Part of the process manager is actually worker creation, and it's fairly simplistic when you work with standard pipes. You just create a worker and connect to it using SLD in, SLD out. With sockets, it's a bit more complicated since you need to have a correlation between the actual process and the socket connection. So you also need to implement some kind of PEAT handshake. And the last part of the application server is the actual load balancer, the most performant critical parts. In this case, what we do, we actually create multiple workers or worker pool. We put them into Leaf stack. In version 1, we use buffer channel for that. When request comes to execute some payload, we actually get first available worker from the stack and pass this request to this worker. If we can't receive the worker in a dedicated amount of time because request is in queue, we can give the timeout error to the user. But in general, request can just wait until first free worker will be available, helping us to mitigate the higher load. If worker processes a request with success, we return this response back to the user or task handler and return worker back to the pool. So it's available for the next request immediately, over and over again. If error happens, then we also need to return the error to the user and need to destroy the worker and create new version using process manager factory and go back to the Leaf stack. So essentially, even if your application dies on request, server keeps working and just creates new worker when needed. Hopefully, application doesn't die, so you don't need to recreate them. At the end of the day, we have the system like that. For load balancing, it appears to be fairly efficient. In general, we have around 200 nanoseconds to allocate the first free worker from the worker pool. It includes automatic recovery, some timeouts, errors, and it handles requests in a blocking mode, so you don't have any issues with concurrent requests for your workers. In addition to that, we implemented a subsystem in the application server, or you'll need to implement it if you want to create your own application server, which monitors all the workers, their memory consumption, their TTL, how much time workers spend for the request, how much time workers spend waiting for the request. You want to have this system because if you have an older application, it might be very hard for you to find memory leak, especially it's a very minor memory leak. So instead, you may just say, okay, I want to limit this worker to 100 megabytes per process. And when it reaches 100 megabytes, please give me a new worker. You typically need to do that before you actually reach the hard limit of memory. So system doesn't even notice these recreations and users does not receive, memory errors. And the last one, which apparently appeared to be the most simplest and boring task, we need to implement HTTP stack. In this case, all we need to do is to implement HTTP or HTTPS listener on Golang, get the request, map it to the appropriate form, in our case, PSR7, pass it to our worker in binary form, process it, and, well, get the response back to the client. Thankfully, the format of the request of SPL library, net HTTP, and PSR7 are very, very similar. So the mapping was very easy. The only thing we had to do is just deal with files and moving them to temporary locations. Again, we can implement it on Golang using SPL library, nothing fancy required. The fact that we use SPL library immediately gives us ability to use a ton of open middlewares and extensions, WebSockets, a lot of the interesting things available by default. And on PHP, we are using PSR7 agreement, which has multiple benefits. Number one, you already have bridges for almost every framework on the market. If you don't have PSR7, you're most likely going to have the bridge from PSR to HTTP kernel from Symfony. It has a ton of extensions, a ton of middlewares, which is very handy. And by design, it's immutable, which plays very well when you're trying to write long-running applications and avoid some unexpected scope leaks. If you want to write a worker, the only thing you need to do is to create a primary loop. You create a RoadRunner client, which receives PSR7 requests. You send this request to your domain layer, and you send response back. That's it. It's compatible with PSR7, 15, and 17. So most likely you can embed your application fairly easily. You can use any routing solution. There is no limitations on that. To run the server, you need a single binary file. So RoadRunner already precompiled. You don't need to know anything about Golang unless you want to listen to the second part of my presentation. You can just install this binary file. You have a simple configuration. You can set how many workers you want. You can configure timeouts, ports. You can actually enable static file serving, so you don't need Nginx at all. You can even enable TSL, and that's it. You can just run your application. It's going to work. It's going to listen on the port you specified. However, in our case, when we've been creating the application server, we wanted to achieve much more than just a simple HTTP. So in our case, we actually build the plugin system, which allows us to configure HTTP middlewares or actually create different dispatching methods inside RoadRunner. And now I'm trying to explain, I'll try to talk which method we actually have. So first of all, that's how typical flow within RoadRunner looks like. You have your handler with maybe some internal middlewares. It converts its request into task. Task goes to the worker pool, goes to the first allocated free PHP worker, and worker processes like that. If worker wants to communicate back to the server, it can use embedded RPC via the protocol we described earlier. So you have two ways to communicate, from server to PHP and from PHP to the server. The first thing which we did on production is actually we implemented GWT authentication directly on Golang. In this case, we can actually intercept request, validate it, and send it back before it even hits PHP. We can connect it to some authentication server directly on Golang. This way, you can handle much higher volume of requests and filter requests which you consider invalid. It's very easy to implement circuit breakers, rate limiters this way. You don't need PHP. You just can use Golang for things like that. Next thing, which we then experimented and later included to one of the releases, is embedded metrics. So now you can have an embedded metric server inside your application server, which allows you to immediately from day one have information about how long it takes to process requests, how many requests failed, and in addition to that, you can expose some of the application-specific metrics from the PHP to outside world. It's very handy when you want to monitor multiple microservices on production in Kubernetes. You can go and create something more complicated. For example, intercept the request and request ID directly on Golang, trace it and record it to some external tracing solution like Graplog or OpenTelemetry, OpenTracing. You can collect logs and send them there as well. It's very handy when you essentially have always run an application server nearby, because you can let the server to do all the heavy loading and caching and sending this request to external solution. One of the experiments we did, we actually implemented a profiling solution using XFProf. PHP just generates the data, sends it to RoadRunner, and then RoadRunner stores it somewhere in database. You can actually intercept some of the requests without even sending them to PHP. For example, some of the things you can handle directly on Golang. It's much more rare use case, but if you have some very highly loaded endpoint and the rest of your endpoints in application are cold, you can just make this endpoint in Golang. Again, it's a rare because we will recommend you just go to multiple microservices, but you can do it as well. However, this approach opens doors for something more funny. For example, you can implement a WebSocket server and WebSocket listener directly in Golang, and then just control it from PHP. We have solution for that. We use it actually on production. In this case, again, Golang creates all the connection pool. It can actually distribute messages through Redis streams, and from PHP, you can just publish them and authorize connections to the WebSocket server. You don't need any external tools, any libraries. You don't need any server providers. It works out of the box. Because you have full control over the way how you create PHP worker, you can actually control all the aspects of this worker. For example, you can control which PHP ini file is going to use, which environment variables you're going to have. Essentially, RoadRunner or application server isolates all of the worker inside itself, so you have full control. If you want to change environments not to a .env file, but using some, like in our case, console or ECDD, you can do that. Just connect it, set the env variables in a process manager, and it's going to work. Our next plan is actually to implement hot deployment, so you can actually tell RoadRunner, okay, this is a zip with the new source code, so RoadRunner will unzip it, configure it, test it, and then make a runtime switch on production to this code. Obviously, you can integrate any Golang library to a PHP code when it makes sense. In our use case, on our production, on our documentation website for the RoadRunner, the search actually done directly in the application server. Specifically, we use Blevo search library, full text library, and we just created a number of endpoints from PHP to index different content. So you don't need any external database, any external service. You can do things like that directly inside application server. And in our case, we are getting fairly small latency on requests like that. It's around a few milliseconds. Because you can, again, communicate with PHP processes using arbitrary binary tasks, you can actually replace all of your HTTP stack altogether. In our case, we tested RoadRunner to operate as Lambda endpoint in AWS. So we used official Golang runtime, added PHP binaries, and voila, we now have the PHP process which is serving as Lambda. Because process does not offload from memory between requests and it stays warmed up around 15 minutes, we are getting very, very low latency on requests. We are not running this approach in production. There is other tools like Brief and other frameworks, so check a look on them, but that's another thing which you can do when you have full control over PHP lifecycle. The thing which we did probably last year, maybe even 2 years ago, and which we run on production right now, we actually changed the HTTP stack to gRPC. So now our requests are not HTTP1, it's HTTP2 protobuf payloads. And now we can actually create applications which communicate with each other using gRPC. So this is a very effective method of passing data between services. It has very low overhead, essentially just operates as a quick proxy between PHP and outer world. On practice, we are getting request latency around 1 to 2 milliseconds with database connections inside. It can also work with HTTP server you have, so you can have both HTTP REST endpoints, gRPC endpoints, or in our case, you can even create some of the services on Golang and combine them with PHP. The thing which we did next and which we use very actively is the special package which allows us to deal with jobs or tasks directly from the application server. The benefits of such solution, because you're able to use Golang, which is way more effective language for like concurrent tasks, to deal with all of your brokers, deal with reconnects, disconnects, graceful shutdowns, delays, and everything else on Golang can, and PHP just operates as a simple handler. It just gets a payload and executes it. In our case, we have ability to run queues from RabbitMQ, from Amazon SQS, from Beanstalk, and from PHP perspective, nothing changes. You just have the same handlers, and if you want to change them to different broker, like from development to production, you just change some of the configuration values. Another small thing that we implemented the queue broker directly in memory. So even if you create a simple, very small application, you still can use queues direct in memory, even on your local machine. You don't need, again, any external services. You don't need supervisor, cron tabs, anything. It's just going to work out of the box, and it's going to work through the application server. Well, there is way more which we can do with application servers when you have control like that. But in our case, we are jumping to the next solution, which we hope to release around Jan or February next year. Specifically, we partner with company and product Temporalio, or previously Cadence from Uber. What we want to implement and what we already implemented is the way to run distributed workflows or orchestration system on PHP. In this case, on application server, we use official Golang SDK to communicate with orchestration engine, and PHP operates the simple DSL, just tells what to do next on a specific step. We expect that this tool will help us a lot to build very complicated and distributed applications for our business. So what is our outcome? The outcome is that now we have ability to separate business and domain level, infrastructure and domain level layers very effectively. We are keeping PHP to do what PHP doing the best, working with databases, working with templates, writing business logic, utilizing our object-oriented approach, and essentially what we used to do for the last 20 years. On a Golang end, we are moving all the fluff which we don't want to deal with PHP. Specifically, we don't want to deal with different type of proxies, load balancing, HTTP endpoints, gRPC endpoints, everything which you just don't care of. Any async algorithms, WebSocket pools, and etc. Golang doing that very effectively. While it's not super effective or super easy to use for the complex business logic rich domains, it's very effective in what it's doing for infrastructure layer. In our case, we run RoadRunner on production for a couple of years so far. When we firstly introduced it to our infrastructure, we managed to reduce latency in 4 times immediately. That's on real application. On synthetics, you can get benefits like 10, 20, 30 times. There is a number of benchmarks available online. We completely eliminated 502 errors and get an ability to actually integrate gRPC communication between our microservices, which we actually run on Kubernetes in Docker images. Because we don't use PHP FPM anymore, it's very easy to put this whole thing into container. It just exposes one port, and it fully encapsulates all of the work with queues, WebSockets, HTTP, gRPC inside one container. You don't need to have any additional tools. And so far, I mean, our rule of thumb is that if endpoint responds like longer than 5 milliseconds, you have to go and optimize it. So typically, we operate about 1-2 milliseconds for inter-service calls. In addition, obviously, that we can reuse keep alive connections. So all of the connection between services to external systems optimized by default. There's been an independent benchmark on one of the Russian websites a few years back. Unfortunately, it did not include a testing for Svuli. We're sure Svuli is going to win because it is using it is not using IPC. It is communicating with process directly in memory. But by this benchmark, RoadRunner beats all the other solutions in performance-wise, especially on a higher load. And it also shows 100% availability under this load without dropping a single request. We released RoadRunner around September 2018. Since then, we are slowly getting adoption. So far, we're about 250,000 downloads, hopefully to get more soon. And our community helped us to create a number of integrations to almost every major framework on the market. We have official integration for Laravel, integration to Spiral Framework, Symfony, UE, Cake PHP Slim, and you name it, I think there is a few others. So what do you need? Why do you need RoadRunner, or actually, why do you need to use application server instead of classical approach? First, if you want to use Docker on Kubernetes, generally it simplifies deployment and it simplifies the way how you can containerize your application. You no longer has to think, okay, do I need to put ingress inside the Docker, or I need to put it in separate Docker? Do I need to connect it to FPM? How am I going to connect it? It works as any other application, just exposes one port. When you want to speed up your application, that's easiest thing to explain. Because the long-running approach, the daemonized application generally work way, way faster. There is only few exceptions, mostly around very, very CPU-bound applications. When you want to have control over PHP lifecycle, when you want to use PHP as some kind of batch processing within Kafka, you want to connect it to any queue, you want to connect it to something which, well, you typically don't have the extension, or you don't want to work on a binary level in PHP. In cases when PHP is just not enough, like nobody is going to be writing a full search engine in PHP, but people are doing that in Golang. People doing distributed hash maps in Golang. People doing a lot of interesting things in other stack. So getting access to this set of libraries immediately opens possibilities to create applications with a bit more fun inside. And well, maybe building something crazy like us, doing distributed workflows, doing the applications which can scale on a very high numbers. In this case, you can move some of the code to Golang, and you can just keep PHP doing what PHP is doing. Or maybe you just don't need to learn Golang at all. Just install a single binary, configure your application, and enjoy the performance benefits. That's about RoadRunner. Thank you for your attention. There is a number of references available in this presentation, which I assume going to be shared after that. So thank you again.